Okay, good morning. So I think it's about time, and we should get started. Okay. So in our previous lecture, we actually provided provided a few very important results for statistical thermodynamics. Okay. So we introduced based on our principles of statistical average and principles of a priori probabilities. We did not postulate, we derived this Boltzmann distribution. So for any microstate, the probability of finding a system in such a microstate is fully determined by its energy. So it's proportional to an exponential minus beta E nu. And of course, beta here is the inverse temperature 1 over kVt. When the state with higher energy will have a exponentially smaller probability of occurring. So this is the Boltzmann distribution. And this very important result, of course, you must have learned this before in your undergraduate course, Boltzmann distribution.
Professor, you didn't share
in our derivation, we sorry, I should share. It's stupid me. I'm sorry. Next time, open your microphone and tell me to remember sharing my screen. Sorry. So I was saying that in our previous lecture, we actually derived a few very important results for statistical thermodynamics. So we derived the Boltzmann distribution, the equation that a probability of finding a system in a certain microstate nu is fully determined by the energy of that microstate. Energy, of course, is a microscopic property of the system determined by the state as well as the Hamiltonian of the system. Okay, and if energy increases, there will be a exponentially smaller probability of finding the system in that state. So high energy state will have less population, and low energy state will have more population. And this is a very important result. And in our derivation, we discovered that this is actually due to the fact that when the system lowers its energy, it must release those energy to its environment. And that increased the number of states, the possible number of states of the environment, and the increase grows exponentially. So you put more energy to the environment, the environment will have a more possible states with the same that amount of energy. So this increases the total probability of finding the system in a certain low energy state. So low energy state, more environmental states, so there's more occurrence, more instances of such states. High energy state, when you pour the energy to the system, then the environment will have a smaller energy and less total number of states. In that case, it's less possible to find the system in that high energy state. So it's due to the number of states in the environment at a given system energy. Okay. Secondly, we introduce this normalization constant Q, the summation all the microstates exponential minus beta E nu, and this is called the canonical partition. T-I-T-I-O-N function. Partition function. Partition function is the center focus of statistical mechanics, because as long as we calculate this partition function, we can generate all sorts of average values through this. For example, we find that minus partial natural Q partial beta at a fixed volume, and the number of particles will give us energy, average internal energy of the system. So this is very useful. Okay, and and then when energy can be calculated, then using our thermodynamic equations, dE is TdS minus PdV plus mu dN. Everything, if you can take derivative of energy, then everything at temperature, pressure, chemical potential, all things, all thermodynamic properties can be calculated. So these two combines from microscopic to, because partition function is calculated from your Hamiltonian. As long as you know the spectrum, you can calculate partition function. Macroscopic to these thermodynamic functions, thermodynamic probabilities can be calculated in this one. So this is a basic prescription for calculating various thermodynamic properties from microscopic partition function. In the last part of our previous lecture, we showed that the standard deviation of energy, because in a fixed temperature case, this is all T, V, N. Fixed temperature, volume, and the number of particles. In fixed temperature case, energy can fluctuate because the system can still exchange energy with the thermal bath. But this fluctuation measured by some standard deviation of energy value divided by the absolute or the real energy value. This ratio actually grows like 1 over square root n. Root n. N is the number of particles in the system. Now, because this n normally is a very large number, so this is essentially this goes to 0 for macroscopic systems. So for macroscopic systems, this ratio approaches 0, and we do not see any fluctuations. We do not see any change in energy. In that sense, this energy can be considered as a fixed value because the change in energy fluctuation cannot be measured. Okay, so those are our basic results, and this actually defines the so-called thermodynamic limit. So actually, those results, as long as you can calculate canonical partition function, you can calculate all sorts of thermodynamic properties. Also, all those results already allows us to apply to different model systems and obtain very important results. For example, we can derive PV equals to nRT from this basic principle. Later on, we will also use applying this principle to calculate, for example, distribution of ions in electrolytes, and that concerns the chemical activity of various ionic species in solutions, and it's very important. So we will talk about this simple Debye-Hughes model for weak electrolyte, dilute electrolyte solutions. Okay, but today I want to go back to the derivation of Boltzmann distribution, and I want to do it again, use a different approach. Okay, and by using a different approach to derive the same Boltzmann distribution, we learn more about the connection to second law of thermodynamics. Secondly, we will learn more mathematical techniques. So actually, from the beginning of this course until now, we have already introduced several mathematical tools, total derivative, different forms of multivariable calculus, right? How we treat different multivariable functions. Its nature in thermodynamics. And Legendre transform, right? The Euler's homogeneous function theorem, this extensiveness of functions, right? And today, what we want to do is we want to derive Boltzmann distribution not from this system-based partitioning and the estimation of a best number of states. We want to derive this from second law of thermodynamics, and to do that, we need a tool called Lagrangian multiplier. It's a tool to do constraint optimization or constraint minimization, maximization. Okay, it's a mathematical tool, and this is also a very important mathematical technique that you should learn, or you should figure it out how to do it. Okay. So to do that, I want to introduce so-called Gibbs entropy. It's a more general form of entropy, and we start from our understanding of what we have already learned, this Boltzmann entropy. And it applies to macroscopic system in microcanonical ensemble. So in Boltzmann's proposal, entropy is determined by natural number of states, number of microstates in this ensemble. Okay, so this Boltzmann entropy requires energy fixed, volume fixed, EVN ensemble. But as we have discussed in the previous lecture, this energy fixed situation is not very useful in our everyday life, in normal experiments, because in our everyday life, normally we do not control energy, but we control temperature. So how do we find an entropy formula that allows us to calculate entropy in different ensemble that's required? So this leads us to so-called Gibbs entropy formula. So it's a generalization of a Boltzmann entropy, of a Boltzmann formula to arbitrary ensemble. So given an ensemble, what we've learned, and a very important point, is that for a thermodynamic system, we do not need to know all the detailed information of the system. We do not need to know with a cup of water. We do not need to know all the position and the momentum of each water molecule in this cup. We only need to know statistics of the system. So ensemble theory states that a system is fully determined. A thermodynamic equilibrium state is fully determined by the distribution. Okay. So when I say P nu is the probability of the newest microstate, and when I use this curl bracket to enclose it, this notation means many instances of P nu. So that is a construct of the distribution probability distribution. So this I denote the probability distribution of a system. So P nu, if you give all the probability for each microstate, and you collect this number, this is a probability distribution. Okay. So this probability distribution should determine entropy. So now we use two postulates. First one is entropy because this probability distribution should be all we need to describe thermodynamic properties of the system. Entropy is a thermodynamic property. So this probability distribution should determine entropy. So entropy S should be a function of such probability distribution. Previously, when we derived this Boltzmann formula, our statement is for microscopic ensemble, the number of states is the only microscopic variable that should be related to macroscopic quantities. So we use omega as the input for a function to determine entropy. And now it's an extension of that idea, because now you do not have a single energy state, a single probability. You have many different states, and each with a different probability of finding it. So this total information described by this distribution should be the input to determine entropy. The second one is the one that we used before. We want extensiveness. E-S-T-E-N-S-I-V-E-N-E-S-S. Extensiveness. This means if we have an independent system A and independent system B, then the total system should be just the quantity, the property of the total system should be extensive property of the total system should be just the sum of the property of A and B. Okay, so entropy is an extensive thermodynamic function. Now, therefore, entropy should satisfy this. So S total should be entropy of A plus entropy of B. Okay. So if this is true, or if we require this to be true, then we introduce distribution of A as P nu. So nu A system state. Nu denotes a system state of A system. And we need another set of distribution for B, and I will use P mu for this. So mu is B system state. Then total system state over any total system state should be, you need to know state of A as well as state of B. So system state will be determined by a probability of nu and mu. You need two indices because you need A in nu state and B in mu state. So this denotes state of A, state of B. Because B is a total system. To determine state of this total system, you need to determine individual state of each individual system. And because A and B are independent. If it's dependent, if they have coupling between them, then this additive condition does not apply. But for thermodynamic properties, actually, for any thermodynamic system, if A and B are in contact, they can couple to each other. But this coupling will be very small compared to the total state of a system. So it will not affect the extensiveness of the total system. So P nu mu, because they are independent. So finding the system A in nu state, and at the same time, finding system B in mu state should be just the probability of you multiply this 2 because independence. Okay. Now we combine 1 and 2. We combine 1 and 2. So SA should be some function of nu, and SB should be some function of P mu. The S total should be calculated from this function of P mu times P mu. But then this must be some function must be additive. And then we apply this mathematical result that in this world, the only thing that allows you to make something multiply A multiply B multiplied by B into something A plus something B. There's only one function that does this. This is named log function. Log function. Multiplication inside log became additive, addition outside of the log. So we now know that this S A should be so we now know that this F, this function, should be some log S in it. And of course, we can have some constant before it. C is a constant before it. Does not matter. So let's calculate S total now. So using this expression. Using this expression. So S total should be calculated. Let me go back here. So this should be some natural log related to some natural log function. So now we postulate, or we say, so how do we do this? F. See. Recall that we say P, we still need to determine the exact form of this F. So there are many of such microstates. This nu denotes new microstate. And the probability of finding a system in it is P nu. So since this F over S must be something determined by natural log, and there are many different forms of this, but we assume, or we imagine that this is actually calculated from some average. So since each state has a probability of P nu, so this function should be also proportional to P nu. Not really proportional, it must be weighted or calculated by multiply P nu times something. And from here, we say this something must be natural P nu, because we want to have a natural P nu, P mu became natural P nu plus natural P nu to have this additive condition. And there are many such microstates, so it's a distribution and we need to sum over all the nu. And this formula should have some constant in front of it. And we want to determine what is this constant. So this is SA. Now SB should be this the same constant times some mu, P mu, natural P mu. Now S total, well, let's verify. Such definition is consistent. So S total from the same formula should be constant times summation mu also nu, then P mu nu times natural P mu nu, because S total is determined by this P. This distribution, composite system. And we know it's independent, so P mu is P nu times P nu. Plug that in, is C times some mu, P mu, natural P mu, P mu. And this is inside nature log, we separate. So this became two different terms. Summation mu, P mu, nature of P mu plus summation mu, P mu, P mu. And now this thing inside nature log is independent of nu. So this summation nu, P nu equals to 1 can be pulled out. So this goes away. This goes away. Then you have we have a summation mu, P mu, because now this is natural. Sorry, this is natural. Careful here. Natural P nu. This nu has nothing to do with mu, so this summation mu can be pulled out. Again, summation mu, P mu equals to 1. Because it's a probability distribution, you sum over all the probability, you should get 1. It should be normalized. And now this is SA. Clearly, now this is SA, and this part gives SB. So the additive condition with this definition of entropy is valid. And this constant is determined by compared to experiment, compared to microscopic thermodynamic variables. Or actually, you can compare this to Boltzmann's formula. And it can be determined that this constant here is actually minus KB. So as entropy for a system with a distribution, if we know the distribution, we can calculate entropy from the distribution. And the entropy can be calculated as minus KB then sum over all the states in the distribution, the probability of a state times nature log this probability. This negative sign occurs because probability is a number between 0 and 1. So nature log probability will be negative. And we need this negative sign to make sure that entropy is a positive valued function. So this is Gibbs formula. This formula allows us to calculate entropy with any distribution. So any system, if we know the probability distribution, we can now calculate entropy. And this is already the most generalized form, most general form of calculating entropy from microscopic distributions. So okay. Any questions here? And this entropy function, or this Gibbs entropy formula, actually can be applied to very general problems. Even in information theory, when people talk about Shannon entropy, it's actually a different form of a Gibbs formula to estimate entropy of anything with a distribution. And you know that from this formula, you can see that if the distribution is broader, more random, the entropy will increase. Entropy will increase because this P will decrease for each different state. If we have more states, and probability of each state will decrease. Then after taking a nature log, it will become more negative, and then this entropy will be a more positive value. So from this sense, that this entropy measures the disorder, the uncertainty of a system, and such kind of uncertainty in information theory is basically the essence of information. As information is about uncertainty of outcome of certain events. Okay,
teacher.
So now with this entropy
ask?
formula, our next task is to derive a new or canonical ensemble. So we already know this result, and the answer is a Boltzmann distribution. But here we want to derive this Boltzmann distribution from a different angle using Gibbs entropy formula. So in a canonical ensemble, we have a temperature, volume, and unfixed. So the temperature is fixed. The temperature is fixed, but energy can still fluctuate. Energy can still fluctuate. So be careful about this logic here. Energy can fluctuate because we have our system and we have its surrounding. At a given temperature, system and surrounding could have a heat exchange. Because you have a heat exchange, so your energy can fluctuate. And this time we kind of show that this fluctuation is very small. Okay. Then Gibbs postulated that in a TVN ensemble, although energy can fluctuate, but the mean of energy is a fixed value. Mean of energy is fixed. So at a given temperature, the average energy should be a fixed value. It's not talking about energy is fixed. No, but its average is fixed. And this is kind of intuitive, and also kind of it fits our everyday experience. But in this case, we need to postulate this. Actually, Gibbs postulated. This is Gibbs postulate. So Gibbs postulated that for a given system in a given temperature, if temperature is fixed, then the average energy is also fixed. Mechanical energy of a system is fixed. So this is a constraint that we need to apply if we want to calculate this probability distribution for a canonical sample. So let's kind of sketch how we want to derive this. We want to derive, because entropy is minus KB, sum over all states, P mu, natural P mu. We know this function. So we want to maximize S by changing probability distribution to find maximum entropy So basically, we want to apply second law of thermodynamics to find this probability distribution, But it's not just applying the second law. We want to apply this second law with the constraint of we have two constraints. It's a probability distribution, so always sum over all states. This must be 1. So you cannot change this p, this probability value randomly or arbitrarily. You must satisfy the normalization condition must be satisfied. So there's in total 1 less degrees of freedom in this distribution. Also, because we want mean of energy to be fixed, like this Gibbs postulate. So the mean of energy means your probability times energy of that level state, sum of the mu, and this is some fixed energy and mean energy, and this is a constant. So we want to, in the end, we want to maximize. We want to maximize maximize this function S with respect to these p values, those probabilities. Because that's what we want to find. We want to find the distribution, probability distribution. Under the constraint of these two equations must be satisfied all the time. And how do we do this? This can be done by using the so-called Lagrange multiplier approach. So to maximize this, let's call this equation 1. To maximize this entropy, what we want to do is, so second law requires that now this entropy so to find the maximum means we need to find the extreme value. Now at this extreme point, all the first derivative should be 0, right? So this must be satisfied from second law. And then we know S equals to minus K B summation nu, then P nu, nature of nu. Let's take the derivative, partial S, partial P nu, will be, you take derivative here, only a single term will go down, but then you need to take derivative of p nu and also derivative of natural nu separately. Okay, so if you take the derivative of p nu, we have minus k natural log nu. K natural log nu. If you take derivative of natural log nu, p nu, sorry, natural log p nu. Natural log p nu. What's that natural log nu? Natural take derivative of this term, and you have a 1 over p nu, 1 over p nu, and you will multiply by p nu, you get 1. Get 1. So this one you have a minus kb. Yeah. And this should be 0. And this is only a single term. If we sum over all the terms, one term is 0, or sum over the term is 0. So sum over everything. It's 0. So we can just neglect 0. We can just neglect its minus sign. And we can as well get rid of this constant. Okay. So this means sum over all the nu and 1 plus natural p nu, then times this dp nu must be 0. We intentionally keep this dp nu here. Means any change, a small change, with respect to p nu. Then we have a normalization.
出口避难逃生，火灾发生中，请勿乘。化学系办报告，化学系办报告。
Sorry about that. Yeah.
火灾报为误触，以上警报为误触，请勿惊慌，请勿惊慌，为粉尘所导致，施工粉尘所导致，请勿惊慌。Fire warning lifted. Please return to your original location.
Okay, there's a false fire alarm in our department, and this is not abnormal. Actually, it happens all the time. So now, from this normalization condition, we can then take derivative. And if we take derivative, you find this equation, all the dp nu must be 0. It's a constant, so take derivative. Its change must be 0. And this is actually very easily interpreted, because this means you can change probability, but if you sum up all the changes, it goes to 0. This enforces the normalization condition. And average energy requires that some nu, E nu, dp nu must be 0. Again, if you have any change in probability distribution, you weighted that by energy, then it's change in average energy, and it should be 0. And Lagrangian multiplier Lagrange multiplier is a mathematical technique to ensure all those equations are satisfied. We introduce arbitrary number, a value called multiplier. So we then solve, instead of solving them separately, we solve a single equation. We solve equation 1 plus some multiplier alpha has equation 2 plus some multiplier beta has equation 3. And we say this must be 0. In this case, because alpha and the beta could be arbitrary multipliers, then it ensures that those two conditions will be satisfied. So we solve this for our p nu, And how do we do this? We just plug in. Those three equations are quite simple. So the first one is summation nu then you have 1 plus nature log p nu plus alpha plus beta e nu beta e d p nu must be 0. So we want to solve this. And the first term 1 here actually goes away because this first term 1 times dp nu. So this term corresponds to summation nu dp nu. And according to our second equation, this is equation number 1. This is equation number 2. This is equation number 3. So 1, 2, 3. Okay? And this goes to 0. So this is 0. We do not need to count this. And this equation is actually a set of equations. It's not a single equation. It's many, many different equations. Must be 0 for any arbitrary change in P. And for this to be satisfied, this part must be 0. So this means nature log P nu. So each term must satisfy this condition, plus alpha plus beta times E nu must be 0. So our P nu then must be something exponential alpha times exponential minus alpha, sorry. So this minus beta E nu. Now this alpha is just a constant, and this constant actually, so the multiplier then, when we compare it to physics, we can know its physical meaning. So this term is for normalization. Okay. And clearly this term can be determined. This term can be determined. Exponential minus alpha should be sum over 1 over sum over exponential minus beta. It's a normalization constant. It's a normalization constant. So it's actually exponential alpha is our Q. It's our canonical partition function. So this is 1 over Q times exponential minus beta. Now the trick here is, then what is beta? We did not at this point we did not define beta equals to 1 over kBt. Okay, there's no such thing here. So this is a multiplier, but what is this multiplier? What does it mean? It has to be related to some quantity in physics. And what is this quantity? So we already derived the Boltzmann distribution. So it's Boltzmann. So you instantly know that beta equals to 1 over kBt, but this must be proved. So we need to show beta equals to 1 over kBt. And to do this, we need some thermodynamics. So first, let's calculate entropy in this new formula, in this distribution. So if this is true, then this entropy of this distribution will be minus kb times sum over new probability is now exponential minus beta E nu divided by Q. This is probability. According to our derivation, it maximizes the entropy. Okay. And then nature log 1 over Q, the entropy, the probability. Again. Okay. And this is then minus kb. We pour this summation the nu and q exponential minus beta e nu out. Okay, and then inside here, we have minus beta e nu, then minus natural log q. Okay, you just expand the natural log. Okay, so this then became, here we have a minus kb sum over nu. This is probability exponential minus beta e nu. Then you have a minus beta e nu here, so it's plus times beta times e nu. The second term is minus kb summation nu u exponential minus beta e nu. Then you have a minus natural log q plus natural log q. And this term, the second term here, actually has a sum over probability here. So this equals to 1. This is kb natural log of q. Kb natural log q. And the first part here then tells us that you have a sum over nu and probability over nu and the energy over nu. So this is the average energy. So this is kb beta average energy plus kb natural log q. So entropy is related to average energy. And in thermodynamics, we know that dE equals to TdS minus P dV plus mu dN, because now we have a TVN fixed. So V and N fixed, so this term goes away. Does not contribute to change in energy. So we have a relation between TD and DE and DS. So we can do this here. This is S, this is E. It tells us that if you take the derivative, then ds dE should give this kb beta. So this kb beta, I use a different color here, the blue color, kb beta, and this T temperature must be the same. If we compare that, this is from microscopic. And this is physics, thermodynamics, must be T. So they must be the same. So we know that beta, kb beta, kb times beta must equals to thermodynamic temperature. Then we have beta equals to, oh, sorry, so I take the wrong direction. You see ds dE, so it's actually 1 over T, should be 1 over T, it's going to go here, 1 over T. 1 over T. Sorry about that. So beta should be kBT, 1 over kBT. So this is a alternative derivation of the Boltzmann distribution, but somehow you see that it's more complicated and it involves more mathematical tool. You need to be familiar with this Lagrange multiplier technique, but it's physically very insightful in a sense that it shows Boltzmann distribution indeed maximize entropy. So when the system reaches equilibrium, the system's distribution and probability distribution will go closer and closer to Boltzmann distribution. The Boltzmann distribution defines the equilibrium points of any system. Okay, so I think that's about it. This will end our discussion on these fundamental principles of statistical mechanics. Okay. So any questions?
Yeah, Professor, I
Please.
have questions.
Speak up. Or hello?
Yes. Professor.
So any questions?
Yeah, yes.
Because I probably see some
Yeah, yes. I have a question about homework.
okay, so there's a question in the chat room. Can you speak up? Can you ask your question? Say it, please.
I already talked, but you didn't understand. You didn't hear it.
I cannot hear you. I'm sorry.
Maybe it happened with the computer.
Because the homework is already. I'll share my screen. So on our class log, I actually post a discussion question on the relationship between Gibbs entropy and the Shannon entropy. So I think this will become a homework question in our next homework that should be given next week. Now, I'm sorry. I think I cannot possibly pronounce your name correctly, but Lauren Go. I don't know.
Yes. You can call me
Can you
Lan.
speak up and let
I already
us know
speak
your
up.
question about homework?
I already
Number
speak
2,
up, but you didn't understand.
right?
Cannot hear something.
I don't know why I cannot hear anything.
Yes, so now you can hear me.
Oh yeah. Now I can hear you. I'm sorry.
Yes, actually have some people, they also have questions you, but you could not hear. I don't know.
I'm sorry. There's some
okay.
some problem about my computer maybe.
It's okay because when I see the question 2.5, I don't understand what they want to do. They want to prove that formula or.
So can you repeat that question again? Or I'm now finding that question. Homework question.
I can share the screen. Okay.
Oh, okay, yeah. Share your screen. That's good. Yeah, please. And tell us about your question.
So the question. See, there was a question 2.5.
Yes.
Yes, in this question, they want to prove this formula or they want to prove another.
They want to prove this formula. They show that this is true.
This means they want to prove this formula.
Yeah.
But from yes, but even with that, for example, with this formula, KT
Yes.
equal. Yeah, yes.
But KT is a constant T, right?
Yeah.
And you can show that for a constant entropy. So a diabatic compressibility means compressibility at constant entropy. Because in a diabatic process, entropy is constant. So instead of KT, you can have KS.
So it means we already have KT, right? We can use.
Yeah, but you cannot use KT to prove KS, a relationship with KS. The idea is, now you want to find something that use entropy as a natural variable, right?
What is the relationship between S and K something?
Can you say that again?
Because I don't know
So
what is about.
above you have a K subscript T, right? KT.
Yes.
KT is the compressibility at constant temperature, isothermal compressibility.
Yes.
Right?
Yes.
But we can define another compressibility. Instead of a fixed T, we can fix entropy. The way we can fix entropy is we perform this experiment at a diabatic condition. If there is no heat exchange, there is no entropy change. So you look at the right-hand side of this equation, 1 over V partial P. This is a definition of a diabatic compressibility. Okay? Yes. So this adiabatic compressibility is made when pressure change, what's the volume change under constant entropy.
Yes. I know that.
Yes.
Because from the question, I don't know they want to prove this formula or they want to prove another formula.
No. So the theorem means only before this exercise, Chandler proved a statement. The statement he showed is this equation from on page 36 from bottom up. You have actually partial P partial V greater or at constant T greater or Z or equals to 0, right?
Yes.
So this means that the isothermal compressibility will always be a negative. So this statement in the end of this page, if the pressure of a stable system is increased isothermally, its volume will decrease. This is a theory. This is a statement about how a system, a stable thermodynamic system, must decrease its volume when the pressure is increased at constant temperature. So David Chandler wants you to show that this is also true for a diabatic process. So you need to prove if the pressure of a stable system is increased adiabatically, its volume will decrease. This is what you want to prove in this question. Exercise 2.1, prove an analogous theorem for the adiabatic compressibility. Okay, so normally I do not explain my question or so understanding the question itself is a part of a test. It's a part of the homework. So you should have a discussion with your students, with other students, or have a what I should say. So what I want to say is, in the midterm exam, I will not give any explanation about the question. You should be able to interpret the question understand what is asked, because that will be part of the exam. Okay.
So actually, without this question, I don't have any confused, but because I cannot see any relationship between the
no,
three.
you should not be confused. It wants you to prove an analogous theorem. So David Chandler just show you a theorem, and he wants you to prove a different theorem for a diabatic condition. So you just need to repeat the derivation using a different thermodynamic function. You want to find a thermodynamic function that has entropy as its natural variable. So you can show analogous equation. For example, for this equation, the third one, the partial P, partial V at constant T and N with minus sign greater or equal to 0. You want to show partial P, partial V at constant S, constant entropy. Minus this will be greater or equal to 0. You just repeat the same derivation. And the key concept here, actually, you want to show something related to fixed S, then you need to find a thermodynamic function with S as its natural variable to do this. So you start with Helmholtz free energy. The natural variable of Helmholtz free energy is TVN. So you end up with a relationship between PV and T, fixed T. And now, if you want to fix entropy, you want to fix S, what do you want to do? You need another thermodynamic function.
I see.
This should not be confusing.
Oh, I see.
Okay.
So after homework finished, can you give us the resolution of the homeworks?
What do you mean?
I mean, after the homework, you can give us the answers for every question, something?
No.
No.
So, you can have a discussions with your friends. Okay, work as a group. And I do not provide standard answers. Yeah. And if you feel like you still do not know the answer, you need to make an appointment with me. Come to my office. I will show you how to do it. Yeah. This is a graduate course. This is a graduate course. Okay.
I see. Yeah. Thank you, Professor.
Anything else?
No.
是，
请说。Okay.
是那个，就是我还没有分组。
Oh, you can join anyone. Yeah, because at this point we haven't have time to do any group discussion yet, so it's irrelevant.
好，
Yeah.
谢谢。
Anything else? So let me explain a little bit more. So I do not give a standard answer because I very much do not want. So this homework questions will appear again in our midterm exam, in our final exam. Okay, and at this level I don't want anyone to actually be able to anyone to just memorize the answer and just copy the answer in the exam. Okay, this happens before. Okay, and for the questions that I give, either it's an open question that you can have multiple or different answers, or the real answer. There's no standard answer to give. Either you should be able to know right away if you answer it correctly or not. So for any derivation, you know that you have reached the result, and it's a good practice to have your to have fellow students, and to have your friends to look at your answers, or you have a discussion with other people. Okay, so we have this group in normally we should have more time to do group discussion, then you have more connection with your classmates. Or if we have in-person lectures, then you have more occasion to interact with your students. In that case, it will you have more chance to talk about difficulties or challenges you encounter in doing your homework. But unfortunately, the situation right now is we do not have in-person lectures, and this semester is such highly compressed. So we have only 14 weeks to work with. So I really do not have much time for you to have more discussions. That's actually not something I want. It's not ideal. It's not perfect. Yeah, but still, I want you to try to interact with other students, or even with me. You make appointment to come to my office. Okay. And really, the so-called standard answer to those questions, they are not really that useful. Okay. And that could be actually very misleading, because normally if you do not understand the problem itself, then even if you see the standard some answer, very often you just memorize it. You do not actually find out what's wrong with your thinking. Okay, with your thinking. At this level of study, that's usually the case. You need to talk with other people. You need to have a discussion to realize what's wrong, or what is the point that you missed. Okay, so you should I encourage asking questions. I encourage you to make appointments with me. So my office is open. Yeah, but I do not want you to see a so-called standard answer, because there is no standard answer. See a standard answer and then just be able to repeat that standard answer in the exam, and that's something I don't want it to happen. Okay. Okay. Any more questions? We have one more week next week, and then we will have a midterm exam. I expect to deliver a third homework next Tuesday. Okay. We will have one additional homework before the exam, and that's mostly trying to help you something for something that I deliver to help with your midterm preparation. Yeah. Okay, so I'm sorry about this problem in my computer. I forgot to turn on my audio, obviously, and sometimes it's confusing to me. And okay, so see you next week.